Hi, everyone. My name is Dan Schrag, and I've been here all day listening to these talks. It's been wonderful to have all of our speakers here, and thank you to all of them for spending this time here and sharing their ideas, their perceptions of this complex problem. And hopefully, in the next 45 minutes, we'll have a chance to flesh some of these ideas out. I'm joined by some wonderful colleagues of mine, starting with the far left, Kerry Emanuel from MIT, expert on tropical meteorology and climate in general. Carl Wunsch, an oceanographer who's moved into all sorts of explorations of climate, and also at MIT for many years, although he luckily spends a good deal of time at Harvard these days too. David Battisti, who we were very fortunate to have as a visitor this entire week in the Department of Earth and Planetary Sciences. David is an atmospheric scientist who teaches at the University of Washington and has worked on a wide range of problems related to climate variability, but also more recently the questions about how climate change might affect food supply. So let me start really with all of you. You know, today we heard from Sue Solomon in the beginning of the day about the question of inevitability and the question of timescale. And I'm finding more and more this question of timescale coming back to a variety of issues related to climate change, both climate science and climate policy. It's sort of interesting, you know, the three of you study climate on different timescales. Kerry, you're known for your work on hurricanes, which have timescales of days to weeks. Carl, oceanography has timescales of days to thousands of years. And David, El Nino, you're sort of in the middle there, a timescale of several years. And yet dealing with the kind of timescale of climate change is still very difficult for all of us. Kerry, you want to reflect on that a little bit?
Well, I can only reflect on it a little bit, and I'm going to turn it over to Carl, who's thought about it a lot more than I have. Clearly, one of the interesting problems that Susan highlighted in her talk was the long time scale response, both in terms of the ability of the Earth system to absorb carbon dioxide that has a short time scale, and actually a whole bunch of time scales. The longest time scales involve the deep ocean, and the ability of the climate system to store heat, which likewise has a bunch of time scales, the longest of which involve the deep ocean. Now, I'm an atmospheric scientist, not an oceanographer, but my understanding of this is that our collective understanding of how the ocean uptakes heat and carbon is not complete. And I think we have to work on that. So that's certainly a direction that we will need for future research.
I mean, I've got to say, I like to think that you used to be an atmospheric scientist, but that you're a climate scientist now. Your own work on the ocean's influence on hurricanes is a nice example of these longer timescales. I think we've all sort of been drawn out of our disciplines to studying this larger phenomenon. Carl, do you want to reflect on that?
It's a very interesting and complicated subject. I think part of the perspective is that we as human beings evolved in a Darwinian fashion to focus on short timescales. And we have to recognize how difficult it is to get people, for example, simply to save for their own retirement. Governments turn handsprings with very complicated pieces of machinery to get people to think a few decades out their own well-being. We've evolved to worry about feeding the children tonight or paying the rent rather than worrying about the long term. And I think this is a large part of the difficulty that scientists and policymakers have with climate. Some of the problems are clearly short timescale, and some of them are the longest timescales that we know about in the ocean. Even beyond the ocean timescale is the memory of the ice caps. Antarctica clearly has some memory of disturbances far in the past. And the discussion, both in terms of the science and the policy, often conflates completely different timescales, very different problems. And I think part of our generic difficulty is there is no forum, there's no mechanism, political or economic, to worry about issues that will work out as being serious problems for our children and grandchildren, the entire political system, our system for funding science, our system for funding startups, getting through the valley of death, is all focused on something of the order of a decade and less. So this is clearly a subject that could take us in any one of a large number of directions, but it's clearly quite fundamental to any serious discussion of climate and climate policy.
I mean, one of the interesting issues, Carl, that you and I have spoken about many times is the challenge of a system that's changing on timescales of a century and yet has observation systems that periodically change every 10 years, satellite systems that change, measurement systems that change, technology systems that change. Part of the challenge is a climate observing system that actually is designed to meet the challenge that is facing us.
Right. So, serious global observations of the ocean start in 1992, and yet we're talking about a system that has memories of past disturbances going back hundreds and thousands of years. And scientifically, this is a very immature subject. Certainly if you believe that observations have anything to do with deciding whether you understand what is going on or what is likely to happen in the future.
And by the way, just to make it very clear, when scientists talk about uncertainty, it's very important to remind people of this. That doesn't necessarily mean that because we don't understand it, the system will not be as bad as some you might have heard. It could mean that it might be a lot worse. So the risk does cut both ways, and that's very important to make clear.
Agreed.
David, what do you think about this timescale issue, the long timescale of climate change versus the timescale over which, as climate scientists, you typically think about both observations and dynamics?
It triggered like a whole set of notes, like I got so much to say now based on what you guys just said. The thing that's both, I guess at one level you could say is exciting about climate change and also quite disturbing is the challenges that are out there. The time scale challenges and the spatial scale challenges are really pretty unique. So if you think about short-term, I mean like next few decades to a century or so, we actually don't know what the amplitude of the change will be. There's some uncertainty. One of the things that the long time scale record tells you is that when we had lots of CO2 in the atmosphere in the past, that the climate change tends to be at least as big or maybe even bigger than what the climate models are telling us. And that's kind of a curious thing. Is the fossil record right, or are the models right? The other thing that you start talking about when you talk about these timescales of response, you're talking about response timescales where, you used to having a drought in one place, drought in another place. The wheat crop goes belly up, I think last year because of in Russia, one of the major producers of wheat, because of a big heat wave and some fires. Those are isolated events. But if you think about climate change, and you think about, for example, the temperature effects on food production, you're talking about it's no longer uncoordinated. It's all places get hammered, basically, in terms of crop production and heat. So it's a little different problem than we've ever had to face in the past. On longer time scales, you even think about what's the response of the ecosystem. Even on short time scales, there's some things that are known, and then there's just a lot about how species interact that you don't know. And so there's a lot of uncertainty in the response, and certainly over longer time scales. When you go to these time scales, you start thinking like, well, how do soils respond? The basic materials that are fundamental to food supply in plants. And these things are just all open questions. They're exciting at one level because they're things that you don't usually think about because they're never things we had to deal with or contemplate that would be happening. So I guess that, from my perspective, almost you could say as a scientist, it's quite exciting because it makes you start thinking about things you never would have considered before because the time scales and the spatial scales that are unraveling with an increase in CO2, we have no human experience in it. It's based on our models, basically. And
well, I think this is actually leads to a question that Kerry and I were discussing just before the panel started, which really has to do with what is the role of climate science actually going forward. There's kind of been an evolution. For the last couple of decades, a lot of climate science has been about, is this happening? What will happen into the future? making predictions. More and more as we move forward, we're going to, first of all, I think many of us expect that the attribution of climate change or the identification of climate change will be more and more obvious. You really will have trouble arguing when there's no more sea ice in the Arctic that climate change isn't happening. The question will be chasing down lots of different phenomena that we observe and asking the attribution question, asking the fundamental relationship question, still always trying to look forward, but actually trying to understand the system. But you know, it's worth a little bit of a reflection that I'd like to hear from all of you of what the role of climate science will be in this discussion and this debate as history moves forward over the next several decades.
There's one narrow point I'd like to make as kind of a preface to the discussion, and that is there's another time scale, which is the time scale over which scientific research can be expected to make progress. And one thing that bothers me a little bit is a disconnect between, I think, the attitude of most scientists about this particular problem and the attitude of a lot of people in the public. Is I think there's an expectation among non-scientists that if we keep beavering away at this, we're going to beat down a lot of the uncertainties in our projections. I personally don't have very much faith that that's so. Certainly, we're going to learn a great deal about the climate system by going forward, and I hope that people who invest, governments who invest in science, will take the broad view in investing in climate science, not put all their eggs in the projection basket, but broadly in things like paleoclimate research and fundamental research, which is really aimed more at understanding than necessarily predicting systems. But an expectation that we can wait until science beats down these uncertainties, I think, is misplaced.
It's possible, and I think even potentially likely, that we will discover that much of the system is not predictable. And though it may take many decades or longer to actually determine that. And so what we have is a very awkward situation for climate scientists in which the political and economic system is demanding answers that to some very great extent we can only answer by saying there are some very severe possible outcomes here, but we are not in a position to tell you that they will happen, or in some cases even what the probability is. And so the science to some extent gets distorted by the insistence that you have to tell us what's going to happen so we can make policy decisions. For much of the science, not all of it, the only answer that the science can give is we can tell you about a plausible range of outcomes. Some of them are very troubling, and you have to decide how you want to live with that degree of risk, or do you want to live with that degree of risk? And waiting, as Kerry says, for the uncertainty to go down is probably a losing game. The uncertainty is quite likely to increase as we come to understand the ever greater complexities of the system. The other brief comment I would make is that 25 years ago, this was what we now recognize as climate science was a small academic endeavor, a few people in universities writing papers that they read and criticized and amplified over 15 or 20 year timescales. Suddenly, this science is in the public domain in which one is being asked for predictions, where often, not always, there are some things we're quite confident of, there are some things that we're very uncertain of, that kind of nuance is often lost. There are some things that if you'd asked 100 years ago, meteorologists, do you think one day we'll ever be able to predict the weather a month ahead? A good meteorologist might well have said yes, once we learn how to do certain things. Today we know that's not possible. It's not technically possible. On the other hand, I can tell you with great confidence that the summer will be warmer than the winter.
Even in Boston?
Even in Boston.
Maybe not in San Francisco, but in Boston.
That kind of distinction between things that we may learn are not predictable and the things that we are quite confident of has been lost in the background noise of this insistence on hard answers from a science that is not yet and may never be in a position to provide them.
So let me just move this in a slightly different direction. You know, we heard from Isaac Held about some of his thoughts about water vapor and precipitation. And we've seen this sort of dichotomy in a lot of different talks. When David Keefe talked about climate engineering, solar radiation management, he showed the results in sort of two fields, precipitation and temperature, as if these are the two main ways that the world is affected. What is interesting is I think a number of us have different ideas about what are the major ways in which society will be affected by changes in climate. David, you've been thinking a lot about crops. You want to start talking about that just very briefly, just in terms of this dichotomy of temperature and precipitation?
Yeah, so I grew up on a dairy farm. We grew corn, and upstate New York. And a bad year is when you have a long duration in the summer where you get less rainfall, and no one was really focused on temperature. That's because it's upstate New York. If you live, say, between 35 degrees north and south of the equator, which is where most of the people in the world live, it's where most of the developing nations are, you're already at a temperature high enough so you're beyond the optimal temperature for plants, for sure, crops, definitely, all except for maybe sugarcane, and quite a few species. So increasing temperature actually adds a lot of stress. And unlike the mid-latitudes where you have large temperature, I mean, the difference between winter and summer is large, right, in temperature. In the tropics, the temperature range is very small, and the variability is small. And if you look in relationship to the projected changes, the changes are actually very large compared to the natural variability. So the reason why people haven't focused on temperature in the tropics is because the temperature's always been too hot, and you just adjust to that, and the plants don't yield as high as they do in other places. Increasing temperature is going to bring crop yields down if nothing else happens, if you can't compensate for that somehow. The other thing which is true, and this is not just in one part of the tropics, this is everywhere in the tropics. The other thing is there's a very basic physiological response. If you increase temperature, metabolism goes higher. If you're a bug and your metabolism higher, what do you do? If your metabolism goes up, what do? You eat, right? So if you're a bug living in the tropics, you eat more, right? So pest damage is going to go up. These are the two major things that the agriculture community, the developing agriculture are worried about, pest and temperature. They both are actually a very large negative impact on crop yields. So this is, I think, one of the things, when I worry about the short-term impact of climate change, short-term meaning over the next few decades, this is something that I think, unfortunately, is a problem that is serious.
And we
doesn't
can
go
point
away.
to the 30% drop in yields that Europe experienced in 2003 during their heat wave in the summer, or last summer in the heat wave around Moscow. It was almost a 6-degree anomaly.
Yeah.
And there was about a 40% drop in Russian wheat yield.
Yeah.
But those are big numbers. And if that heat wave had hit Chicago instead of Moscow, U.S. corn harvest would have been about 40% down, and that would have been a big deal.
Yeah.
At the same time, conventional wisdom is that temperature isn't the only thing that affects people. Kerry, do you want to,
Well, I would only add to that, and this is stepping out of my expertise, that I think what David has just said illustrates, among other things, a sort of disconnect between metrics that we scientists use internally to talk about how the climate system is changing, and metrics that might mean more to people about what the impacts of the changes are. So with respect to crops, I happened to read a few weeks ago a report that was commissioned by our Defense Department about security issues arising from climate change. It's a real eye-opener to me. Some of you, I'm sure, are familiar with this report, but they're extremely concerned about the agricultural impacts, both from the point of view of food production and also just the supply of fresh water to people, the potential of that to trigger political conflict around the world. And something that David Keith mentioned, I think, at the end of his talk about what he was personally concerned about in climate change. When you start thinking about the fact that the world is built out as much as it is, and it's so almost saturated in its agricultural production and optimized to today's climate, any change can be destabilizing that way. I don't know how you build a metric of that into climate projections, but surely someone should try.
And those kind of, maybe they're first order effects, but they're complex interrelationships that lead to these results, very difficult to study. A nice example is the El Nino event in the 60s that created a drought in Indonesia that was at the same time as the major coup that threw Sukarno out of power and brought Suharto in. I don't know how many people in the audience have seen the movie The Year of Living Dangerously, old Mel Gibson movie with Mel Gibson and Sigourney Weaver. It's a wonderful movie about this transition.
Yeah, that's right.
It was a time when Sukarno was making nice with the communists, and it fed into our view of the domino theory that essentially the whole of Southeast Asia was going to be given over to the communists. And yet there was a drought, people were hungry, that supported the Communist Party, there were uprisings, and the communists led a coup in Indonesia. Sukarno was the president. They threw Sukarno out. Suharto, one of his generals, came in with a counter coup and slaughtered several 100,000 people. And as a result, Indonesia was no longer in danger of turning to communism. The question of the role of climate in El Nino in that, what was the role of the drought in that transition? It would be silly to say that the drought caused the political chaos of Indonesia in the mid-60s. At the same time, it certainly played a role, and that, I think, is more likely than not the way it's going to be moving forward. Climate is going to be added to a set of additional stresses, whether it's groundwater or overpopulation or a variety of economic stress, and exactly how the climate interacts with all of these is a very difficult subject. Is that your sense as well, Carl?
Well, if I put an oceanographic hat on for a moment, one of the areas that is usually skipped over rather quickly is the acidification problem. And I don't want to say much about that because one of the dangers for scientists in climate discussions generally is stepping out of what one really knows. But I've heard enough from colleagues to suspect that ocean acidification and the sort of geoengineering fix that David Keith so nicely described would do nothing for that. The biogeochemical system is sufficiently complex that if you really are looking for tipping points, that's where you perhaps might look. The other area where I do know a bit more is sea level, which actually embodies the timescale problem that was talked about before. Those of you who read the Boston Globe, a week ago Sunday, top of the front page, something about rising sea level endangering New England, and it was quite clear that they had utterly confused the very slow growth rise in sea level, which is a serious problem for some places, like
including Boston,
Bangladesh, with the problem of storm surges, tsunamis, other high-frequency phenomena. And this was all rolled together in one package about how something had to be done about rebuilding seawalls, which is probably true, but for a quite misguided discussion of what is the role, for example, of the melting ice sheets vis-a-vis the probability of more frequent hurricanes or northeasters, and with no mention whatsoever of one of the big elements of the climate problem, which is also usually set aside, the growing human population, both in numbers and redistribution along the coastlines. If one wants to ask what is the major climate change driver, you might put population at the top of the list, and we almost never talk about it.
So I want to just, follow up on that ocean acidification comment just very briefly. I've got to say, as somebody who's spent a lot of time studying coral reefs, ocean acidification is certainly a terrifying prospect because it may well do away with coral reefs, at least as we know them today. That being said, I've always felt that it was a little bit of a red herring in the whole climate discussion, not because it isn't serious, but because we're unlikely to do anything about it. If you look at if you really cared about ocean ecology, the first thing you'd take care of is overfishing. If you look at any of the studies of marine ecology, we've decimated the oceans by pulling too much fish out of the ocean, and we don't seem willing to stop. And the idea that we're going to change our behavior radically because of ocean acidification seems naive, unfortunately. I wish it were compelling. It certainly scares people, but it's not clear that it actually...
This again, though, is the kind of the interface between what the science is trying to say and what you might actually do in public policy. They clearly overlap, touch, but they are not the same problem.
That's
and
right.
I would agree with you.
That's right.
But you can undo overfishing if you want to, right? But
Maybe.
But it's pretty expensive. I get, it might be, this is not my expertise, but if you acidify the upper ocean, it would be pretty expensive to figure out how to undo that. It's not my expertise, so I'm not going to comment.
could
But
wait.
you could wait. You could
You pretty much
wait
have to do that with overfishing, too.
a few millennia, like.
No?
Well, no,
faster
not
than
for the
that.
CO2, but I'm thinking for the
It's
climate
a little
change.
faster
Sorry,
than
sorry, not for the acidification, but for the climate change aspects, you're waiting millennia,
Yeah.
which raises another. Okay, so for me, there's a couple things not to lose track of here. I think, as Carl said, we're going to work hard as climate scientists to do our science because we love our science and we learn a lot about the system. And I think most people would agree, most of the best people in the field would agree that we're probably not going to make any useful progress in terms of reducing on uncertainty. We'll have little victories here and there, but they'll be small. I'm sure that someone said at the beginning, that we knew roughly what was going to happen if you doubled CO2 over 100 years ago. And actually, this field was relatively small until, in my experience, until the early 90s when a statement came out, the balance of evidence suggests there's a discernible influence on humans. I think a lot of people in my community actually thought that was a stretch. And that gets you excited as a scientist. I want to rip that apart. Data aren't good, models aren't good. Can you really say that? That doesn't detract from, I think, what Carl was saying is the big picture. If you double carbon dioxide in the atmosphere, it's going to warm. Someone told me in my beginning days of graduate school, I can't remember, I wish I remembered who told me this, and I wish I'd written down the quote, but climate is 9 parts radiation and 1 part circulation. The circulation part, winds, currents, tides, that's hard to figure out the details. But if you just put a blanket around the Earth, the surface is going to warm up, and we've known it for a long time. And so there are things that we can say with some certainty, and we can have a range of projections of things like global average temperature or even temperature on a pretty large scale. And there's things we just won't be able to say. We're going to work on it. The issue, though, of the global extent of this change on things like, I think, crops, and in particular ecology, you acidify the ocean, you perturb the very base of the marine food chain. You change the temperature and humidity and precipitation patterns of the surface, and you change the very base of the ecological terrestrial ecology. And I don't think we'll be in a position to understand that response until we actually just see it and then try to make sense out of it. The other issue at the time scale is, of course, you live with this for thousands of years, some aspects of the temperature effect of the atmosphere, for example. And then it raises issues of, David talked about, I'm sure you brought this up in your talk. I'm sorry I wasn't here. I've seen parts of it before. The issue is for me, the most interesting issue of geoengineering, there's going to be uncertainty in the response, probably more uncertainty than in the CO2 response. That would be my bet. That's if I'm not betting on it, but so far that's what we found anyway. But what the interesting thing for me is that you're talking about now managing climate for millennia. And I can't think of anything humans have done systematically for a millennia timescale. And so the question is, can you pull that off?
Well, so it's an interesting thing. So let's talk about geoengineering, although I've got to say, it was sort of interesting how the program was organized, and I was on the organizing committee, so I take full responsibility for this. But it was interesting how Michael and David, David first talked about geoengineering, and then Michael talked about energy policy. For the most part, when I think about the problem, I think about, first, energy policy, can we actually reduce emissions? And then second, okay, if we can't, and we think climate change is going to be intolerable, then maybe we think about some of these questions about solar radiation management. It's interesting how these were reversed. You'd like to think, now, as it turns out, we would have gotten there anyway, because Michael's talk, I would say, was not particularly uplifting or optimistic. I do want to just respond briefly, and we have a climate science panel up here and not an energy technology or policy panel, and so we just apologize to Michael for that. But I do want to say, though, that this is a 100-year problem, and there's both good news and bad news about that. The long time scales that Sue talked about this morning are partly scary because they're so long and so difficult to comprehend and deal with. At the same time, it also means that we also have time. That doesn't mean that emissions now don't matter. Emissions now matter very much, but it's a cumulative problem over 100 years, and the way I like to think of it, and this is really just me trying to make sure I can get out of bed every morning, is that it's a 100-year war, and if we lose the first 2 decades of battles, it's a terrible thing, but it doesn't mean the war is over. You keep fighting, because ultimately it's a 100-year war. And I think that's an important perspective. Certainly climate politics and policy doesn't look terribly bright right now, and I would say we've lost a bunch of major battles, but it is at the beginning of the campaign. Hard to imagine, but it is important to remember. Now, when it comes to geoengineering, David, Keith, and I had a workshop here at Harvard now 3.5 years ago. It was a long time ago. But all 3 of you came, and in some ways that was one of the first times where the 3 of you really engaged on this issue. In thinking about that today, and I know all of you have, to one extent or another, thought about this a lot more since then, where are you now on the idea of intervening in the radiation budget of the Earth, potentially to combat climate change? Kerry, why don't we start with you?
The point that David Keith made that's worth re-emphasizing is that some of the techniques that have been talked about and seem very plausible are also very cheap, which means that small countries, maybe even a rich individual, could try to do it unilaterally. And if for no other reason, we need to understand this problem. We really need to study it, understand much more precisely what would happen so that we understand the risks behind it. I would say in the 3.5 years since that workshop, in my own mind, the probability that this will eventually come to pass, that we'll implement this, although still small, is larger than it was 3.5 years ago, simply because the alternatives seem less probable.
Carl, do you want to reflect on that?
Well, I find the prospect rather scary, because it strikes me that here's a very complicated, very nonlinear system that we don't fully understand, and now you're going to start poking it. Of course, we already are poking it by emitting CO2, but it strikes me as a bit like turning the controls of a passenger airplane over to somebody who's never flown before, and simply assuming that because it's been flying in a straight line, it will continue to do so.
But we already did that.
We've already done that.
We turned it over to the energy companies to fly. So.
And I would say in the 3.5 years, at least personally, I would say, I more and more understand how complicated this system is, how little is understood of what will happen, and in particular, what will happen over timescales that are long compared to 3.5 years. One of the scarier statements that I heard was from a Department of Energy undersecretary, which is he thought, a good 10-year research program would tell us enough about how the climate system behaves to permit us to understand what would happen if we started to intervene. And I said, you're a physicist. Here you are, you're dealing with a system that has timescales.
Luckily, that doesn't tell you anything about which undersecretary said this.
Doesn't matter.
They were
Mr.
both
Smith,
physicists.
They're all the same, yeah.
tens, hundreds of thousands of years are embedded in this system. Do you think 10 years is enough? Well, we changed the subject at that point. But I share the sense that people will be tempted to try things, and it's very worrisome. You can make things worse. There are many examples where intervening in systems you don't understand has made the situation worse.
I mean, I still think, Carl, that at least what we know now, and we need to know a lot more, but I still think of it the way Churchill thought about democracy, that it's the worst form of intervention in the world, except for.
I would fully support what I think is part of David's point, is we've got to understand what the possibilities are. And it may end up, as other people have pointed out, a situation where you have a terminal cancer patient. You've tried everything that medical science says helps. You've run out of options. And you say, well, here's something that could conceivably work. We don't know, but we're so desperate, we might as well try it. I think we need to know what the possibilities are. A decision about whether to do something in desperation is going to come back to the political world, not the scientific world. It's like in a medical decision where you have a family involved with doctors who say, we've tried everything. Here's an idea. The patient could be made to live a little longer. The patient may be cured. The patient could be made desperately uncomfortable. What do you want to do? It's not science.
Yeah, that's right. I mean, one of the things that both fills me with enormous optimism and also enormous pessimism about the future is the incredible adaptability of the human species.
People will survive. I mean, I'm pretty sure the human race will survive, although whether civilization will look much the way it does now, 1,000 or 500 or 300 years from now, I won't go there.
Well, in some ways, I mean, that's right. The optimism is that this is, humans are incredibly good at adapting to situations, and we will find a way to adapt to climate change. That isn't to say many, many people won't suffer tremendously, especially the poorest people in the world. Although I've got to say, we're not doing such a great job taking care of the poorest people of the world today. There are a lot of people suffering already. But more will suffer because of climate change. At the same time, because we're so adaptable, the urgency to act at a grand scale at any one moment in time, even as climate change proceeds, will be very difficult. It'll be difficult to mobilize the kind of will to profoundly change our systems. Maybe this is a good time. We only have a few minutes left. Maybe this is a good time to ask if there are any questions from the audience for the panel. If you could line up here behind the microphone, and then keep your questions very brief, because we do only have a very limited amount of time left. No comments, just questions, please. Thank you.
Uh-oh.
Do you have a question?
I'm strongly moved to say that the analogy of a war that can go on for 100 years with 10 bad years at the beginning, but it's not over because we can keep fighting, is not a safe analogy for us to start thinking in. I think that the human race and civilization as we know it, the environment that has allowed us to evolve to this point and permit civilizations to begin and flourish, that time might be over. And that many of us need to turn to thinking about what's being called transition towns, with the effort to adapt, to create a resilient community that can work together no matter what happens to try and help each other survive. Thank you.
Thank you very much. I think there's all sorts of important efforts aimed at creating resilience, improving people's ability to adapt to climate change, as well as many other environmental changes. That being said, scientifically, I think many of us feel that it's dishonest to say that somehow in 10 years the sky is going to fall, and that often there are some people who claim that if you don't do something in the next 5 years, it's all over, you can throw up your hands and give up. And I don't think that's true. I'd love to hear your thoughts about this. Kerry?
Just
or-
very briefly, I mean, I think in other fields where we're all familiar with assessing and dealing with risk, like when you buy a property insurance policy, one thing you learn is that people have, across all kinds of people, all sorts of perfectly rational people, there are completely different attitudes toward risk. There's very risk-averse people, and there are people who are willing to tolerate a lot of risk. That's not going to change. And I think that's part of the reason why there's such a vigorous discussion. There are sort of low probability events, at least they're low probability in the minds of climate scientists, that would be truly catastrophic. Maybe not on a 10-year time scale, but out to 50, 100 years. People say, well, it's low probability, let's not think about that. That's one attitude. Other people will say, well, we'll do everything in our power to avoid that. It's
Although
just part of the human
Although there is a
condition.
complication with the scientific community, essentially, we're used to 95% confidence intervals before we actually are willing to say anything. And the world doesn't work that way. I testified once before Congress next to a former five-star general, Gordon Sullivan, who I was talking about this problem of 95% confidence intervals, and he looked at me and he said, in the Army, we don't even wait for 50% confidence. He said if we did that, we'd lose far too many lives. We look at the trends and use our best judgment, and that's how we make decisions. And the trends in climate don't look so good.
Yeah.
And that's really the point, I think. Anyway, please, next question.
Thanks. Yeah, exactly. The precautionary principle really should be the basis of how we act on such an issue of scale of human existence itself. And I just want to comment earlier, you said something about, people didn't even stop overfishing, even though we know that overfishing is depleting fish stock. Something like 30% of the fish stock in the ocean is already gone, like a couple years ago, right? And then you say that that's why you think it's hard to stop acidification. I think that actually, that fact that we haven't been able to stop overfishing and we're not able to stop ocean acidification as of now is totally a reflection of failure of educating the public in the proper way, meaning that we're not actually, as scientists as well, but also the media has not, and especially the politicians have not been being totally forthright in, really speaking about the seriousness that it's threatening our survival.
I get your point. I know this question versus comment thing is not working. So let's just please let's
Okay, I
answer the
have
question.
one question as well.
No, I think you just asked it.
Okay.
Didn't you just ask the question about? I was going to let the panel answer.
No, I have a question about the time scale.
Okay.
About ice sheets, because Dr. James Hansen wrote in a paper in 2008 that, in fact, the generally held belief that the disintegration of ice sheets would take on the order of millennia is actually not necessarily true, because it's more likely that the reaction to the forcing is actually from the ice sheets is actually very fast, judging from the fact that in local insulation disturbances could cause very quick changes, and the fact that previous slow millennia scale change was more likely due to the orbital changes that itself took thousands of years. What do you think?
So Carl and Kerry and I have all thought a lot about sea level. Carl, why don't you take this one?
Ice sheet physics involves timescales ranging from minutes, interactions with waves, to millennia and beyond. And this is one of the reasons why ice sheets are so interesting. There are all kinds of timescales involved. The ice sheets last for hundreds of thousands to millions of years. Their edges break up, sometimes in a matter of days. And this is a considerable challenge. You have to take into account all of the timescales from seconds, minutes, hours, days, out to millennia. That's why climate science is so interesting.
So both Carl and I, and did you come to that workshop
Yeah.
a couple of years ago we had here?
The sea level one or
The sea level one we had here?
No.
Oh, Carl was there. Elliot Zipperman and I ran this workshop, and we had really assembled some of the best glaciologists in the world and spent a long weekend.
yeah.
You were there.
Oh, you said glaciologist, I remembered, yeah, okay.
Yeah. And we spent a long time really listening hard to some of the best glaciologists in the world, thinking about both Greenland and Antarctica and their future in relation to thinking about sea level rise. And I think where I ended up, and Carl can correct me, but I think first of all, yes, there's great uncertainty about all of it, but the uncertainty was a lot different than what is portrayed in the media and is portrayed by Jim Hansen's comments. First of all, in Greenland, where there's about 7 meters of sea level equivalent stored, people talk about the glaciers collapsing and the ice sheet falling off into the ocean, and in fact, that's actually a limited problem in Greenland because there's not too many locations where that ice can actually touch the water. And the big question is really the surface balance, the question of melt pools and what the color of the melt pools are on the top of the glacier and how that affects the radiation budget and how much melting occurs. But that overall, it's very difficult to imagine more than maybe 20 or 30 centimeters of sea level rise over the next 100 years. Beyond that, it certainly could accelerate, but that it's probably difficult to see how that's going to happen. Big uncertainty, but that it's not something to panic about just yet. In Antarctica, it's very interesting. It's the opposite. It's not the ice melting, because Antarctica is so cold. In fact, it's the big ice shelves breaking off that are holding back large ice sheets. And there, it's an oceanographic question, and that was the irony. We were gathering with all these glaciologists, and the main uncertainties in Antarctica have to do with the ocean and how much the ocean will melt these ice shelves. And there, the best observations come from thermometers strapped to seals. And we essentially don't have good observations that we need to make even a decent oceanographic model of what's going on there. And I think, Carl, you'd probably agree with that.
Yeah, I think the one, there may be surprises out there. I mean, if an ice sheet disintegrated within this century, that would be a real surprise in the sense that everything we've seen suggests that that's really out of the question. If a big enough ice sheet if you want to say, are you going to get a meter jump in sea level, that might be, 300 or 400 years off. We have no idea. And if you're going to, I think at this point, make an argument that we need to act because of that, someone needs to act because of that, then it's basically, it's not grounded in science. Okay.
At the end of this century,
One more question?
But there are things you do know. You do know that there are slow changes. Temperature is going to go up. Sea level on average is going to go up. And these things are inevitable. You also know that to do anything about this problem is going to require just reducing the total amount of carbon dioxide that has gone into the atmosphere between now and whenever. And that, for reasons that Michael was talking about, technology transfer and new energies is a really slow process. And so I think we need to be thinking about what can we count on in terms of the long-term implications if we get another X amount of total carbon in the atmosphere, however it's put in, and we have this basically this freight train, this ocean liner. It's going to take a long time to stop it and slow it down, basically, and you have to decide what are you willing to live with that we know about. And this is a very individual thing. It's a risk thing. We should be discussing this not in terms of an economic argument or anything else. This should be discussed on it's a value system argument, that we should be having that argument and that discussion based on the science. The science can inform that with the things we can say. There's a lot of things we'll never be able to say, or at least not in time to actually make a significant difference.
James,
Okay,
last question.
hoping for a little more clarification here. Given what each of you has been saying about uncertainty and risk, could you respond to what Dan said when he quoted the military guy? 50%, and we go forward because we look at the trend. Because I sort of feel like I'm listening a little bit, we're burning up the planet. I have this idea in my head of a cartoon. We're burning up the planet, and there's a panel of scientists, and each one is saying, it's not my area of expertise.
Well, there is one place where I think there is something that scientists can say and do here, to answer your question, is to quantify the risk, and we have tried very hard to do that, quantify the uncertainty of the risk. And this is the hard task that we haven't been very successful, is communicating that. I think it's not our job to decide what policies and so forth to implement. It is part of our job to convey that sense of risk, including, very importantly, the uncertainty in it. It could be a whole nother panel discussion. We haven't really succeeded as scientists, I would argue, in conveying the risk to the public. How do we do that better?
If we were sitting up here not as scientists, but as citizens. And you said, what should we do on the basis of the trends? I suspect, without putting words in other people's mouths, that most of us would say we should vigorously work for emission controls, try to understand how we could remove carbon dioxide from the atmosphere, and so forth. But I think it's very important to try to distinguish what the science says and what we think good public policy is on the basis of what is known and what is very uncertain. That was not the questions that were put to us.
So the other thing I want to, it's a little bit, it refine maybe what Kerry said, and maybe you agree with this. That, one of the reasons why you don't hear us talking about what to do or anything like that is because actually most scientists are still really scientists in the sense that we do try to distinguish between trying to understand the world better, reducing uncertainties, and if you're expecting us as scientists to assess risk, this is where I just want to think the language is important here, that's wrong, because risk implies probability times consequence. Consequences implies values, right? And all of us are scientists, and we don't feel our training is that our value system. The reason why maybe Carl might appreciate occasionally something I do in science is because I do it well and rigorously and objectively, and at the end maybe he can walk away from the center and think like that's probably true, and that's a really important part of our culture and how we're accepted in our culture and what makes us good if we're good. But to say then what's the risk of something happen? Well, I could work with someone in the financial community, but that's because I'm using somebody else's value system to multiply my uncertainty by to come up with the risk, right? And you won't hear most of the people in the science community doing that because one is we don't know anything about those. We can pair up with people, but even so, when we do pair up with people, it's like, what's the likelihood of you having a good rice crop in Indonesia? Well, I have to belly up with an agriculture person and probably an economist in Indonesia to do that. That's still fine. That's a very neat intellectual thing to do. What you would do with that information is a value system, right? And we stop there because not because we can't do it. Carl could just and I could tell you what I think we should do, but that's my own value system, and I don't have any special platform for that, right? Everybody in here has a value system, and we all come with our special knowledge, right? And our knowledge and what we actually enjoy doing is the science part of it. And so I think you're not going to get it if you expect to get it from a community. That's what we have to straighten that message out really clearly because we don't want to do that.
So let me just end this panel with in answering James's question again. Sort of in some ways throwing it back at you, James, and against everybody in the audience, and that it's really all of our responsibility here. Yes, there's a question of communication of the science. There's a lot of effort. Sue Solomon has spent the better part of the last several years working on communication of science to the broad public through the IPCC, and many, many people spend a lot of their time working on this communication issue. At the same time, the public, many of them do know. I mean, I think John Krosnick's survey does show people are actually familiar with this. It's not that they understand it completely, but they know what's going on. They're just not willing to make changes. And they're not willing to make changes even in the voting booth. And I think that for me, James, I was taken by Senator Bingaman, who was here for his 40th Harvard anniversary last year, was on a panel with me and a few other people talking about climate, and he was the last to speak. And we were all talking about the need for action in Congress and the failure of the Senate. And he's the chair of the Senate Energy Committee. And he said, I would love to see action on this. This was shortly before he announced that he was stepping down from the Senate. He said, I'd love to see action on this. He said, I've been fighting for this. He said, but I'll tell you a story. My colleague in the House is running a campaign in New Mexico, and his opponent, the main attack ads on television are saying that he voted for Waxman-Markey. And he's losing. And he lost. When the politics are such that supporting action on climate change is a recipe for getting voted out of office, we're not going to see change. And that's the bottom line. That's the sea change that has to happen in this country. And yes, scientists are responsible, but I think we're all responsible ultimately for making that change. So thanks very much.
So I'd like to thank the panel for an excellent discussion and a way of summarizing the day. And I'd like to thank all the speakers for giving really wonderful talks covering a wide range of issues of climate change. And I particularly would like to thank Dimitar Saslov, whose idea this was, and the whole planning committee for setting up this symposium. I'd like to thank Becky Wasserman and Phyllis Strimling for making this possible. And I'd like to thank Barbara Gross, the Dean of Radcliffe, for all her inspirational leadership. And thank you all for coming. And there will be a reception downstairs, and you can continue to talk there. Thank you.